Hi everyone, welcome back to statistics and data analysis. So starting from today, we will use 2 weeks to introduce probabilities to you. Okay, we will talk about the basic mathematical concepts about probabilities and how may we apply them to solve some problems. And then these ideas about probability will be the foundation for you to learn some advanced topics later in this semester. Okay, let's start. So let me give you one example about statistical inference to help you get the idea about why do we need probabilities. Suppose we are running a factory and we are producing LED lamps, okay, for a whatever brand. And then our question is about we want to know a number which is mu. Okay, this number is the average number of hours that an LED lamp is functional. Okay, for different LED lamps, they may have different number of hours of life. Okay, and we want to know what's the average of all those numbers. So if we produce 10,000 or 100,000 of LED lamps, then we know for that particular set, the mu is a constant. Okay, it's just that we don't know, and we cannot test all those produced LED lamps, because if we want to know the length of life of each lamp, we need to keep running it until it is burned out. So we cannot destroy everything we have produced. So all we can do is to select a random sample, let's say 40 or 100 lamps, and then we test this random sample and get a number, okay, x bar. X bar is sample average or sample mean. X bar tells us that in average for these 40 lamps, the total length is 28,000 hours. Okay, so intuitively, there's one thing I can do. I can simply say, let me guess. Mu is exactly 28,000. Okay, I guess mu is just equal to x bar. Population mean is just equal to sample mean. I can certainly make that guess, and then I want to know how likely I will be right. Right? If I can say with high probability my guess will be true, then that would be a good guess. Or if I can know the probability for me to be right is very low, then I probably need to adjust my estimations. So that's one possible thing we may do, and we want to know what's the probability for me to be right. We probably want to do some other estimations because the previous estimation is quite unlikely to be true, right? We just guess one number. It's very hard to really hit the target mu. So probably we want to ask, maybe mu is in between 27,000 and 29,000. Again, we want to know how likely we will be right. Or if we enlarge the region a little bit to become 26,000 and 30,000, we probably can say that the probability for we to make a correct guess for the third trial would be the largest. Okay, but of course, because the region is just larger, but we want to know how likely we will be right. If this has a very high probability, say 90%, then probably when we are making the guess, we should produce a smaller interval, right? We want to do a trade-off between high probability and large interval about estimations, and all of them require probabilities. We want to have a large enough interval with high probability to be right. And then we really need to learn probability. We really need to learn those mathematics for us to be able to do all of this. Okay, this is just one example, and we will see more. So today my plan is that I will do basic concepts in the first videos, and then we will address specific topics in the following 3 videos. So first, let's talk about some basic terminologies. Experiments and events. Suppose I am doing an experiment. What does that mean? That means I am running a process that will produce some random outcomes. Okay? The key here is that we only care about random outcomes, because if the outcomes are just certain, then there's no reason to do probability. Okay? Some examples are here. If I toss a coin, then the outcomes may be head or tail, but I don't know. Okay, before I do it, I don't know. So this experiment is creating random outcomes. Or probably I want to test what's the effect of a new drug on a new patient, and the outcome may be the drug is effective or not effective, or even make the patient getting worse. There may be even some more possible outcomes. Probably I interview 20 consumers and ask them how many of them would be willing to buy a new product. Okay, I'm doing a market research. Some possible outcomes are here. If my product is really good, then probably 20 of them would like to buy. If it's quite good but it's quite expensive, then probably 15 will buy. If it's just an okay product, probably 10. If it is a very worst product with very high price, probably no one wants to buy it. So the outcome of this survey may be any integer between 0 and 20. Okay? And before I really find 20 persons to do this survey, I have no idea what will be the outcome. The outcome is certain. Finally, I probably want to sample a few bottles of ketchup and estimate the weight. Okay, estimate their average weight. And the outcome will just be all those possible numbers about the weight of each bottle of ketchup. Okay, again, the key is that randomness. For an experiment, we define something called an event. An event is just an outcome, a possible outcome of an experiment. Okay, we will call it event. For example, when I toss a coin, then one possible event is to get head. One possible event is to get a tail. Each event would have some probability to occur because outcomes are random. So for each event, there should be a positive probability. And that's the probability for us to see that event to occur. For example, when I toss a fair coin, then with probability 1/2, I will see a head. With probability 1/2, I will see a tail. If I am rolling a fair dice, then for probability 1/6, I will see 1. With probability 1/6, I may see 2, and so on and so on. For each possible outcome, the probability is 1/6. That's just the chance or the likelihood for us to see that outcome. So about notations, suppose we use A to denote an event of an experiment. We will write PR of A, which just means the probability of A, to denote the probability for this event A to occur. Okay, so we call this a probability function, which translate event to probabilities. Okay, for example, if A is getting a head when I toss a fair coin, then probability of A is just 1/2. This is how we express this probability. Some events are special. We call them elementary events. An elementary event is an event that cannot be decomposed into smaller events. Okay, so they are elementary. Some examples are here. Suppose I am rolling a dice, then getting 3 is an elementary event because you cannot split it into smaller events. Then there must be some non-elementary events, right? How about getting a number larger than 3? A number larger than 3 may be 4, 5, or 6. Okay? And then immediately we can see for this particular event, there are 3 elementary events. I may get 6, I may get 5, I may get 4. Altogether, that's the event for getting larger than 3. Okay, so getting larger than 3 is not elementary. How about the event of getting larger than 3? Okay, as we say, this can be decomposed, so it's not a elementary event. How about getting an even number? An even number means you are getting 2, 4, or 6. Again, that's not an elementary event. For another example, suppose I ask Jane, Mary, Melissa, and Lucy about a new product, and I ask whether they want to buy it or not. Suppose I am saying that there's an event. 1 is willing to buy. 1 out of the 4 is willing to buy. Okay, that's one possible outcome. And then, is this an elementary event? Well, the answer is no, because this 1 may be Jane, or maybe Mary, or maybe Melissa, or maybe Lucy, maybe one of them. So this event can be decomposed into 4 elementary events. The first elementary event would be Jane wants to buy it, but all the other 3 do not. The other is Mary wants to buy it, but all the other 3 do not, and so on and so on. So this is not an elementary event. As I just mentioned, if I say Mary is willing to buy, but all the other 3 are not, then this is an elementary event. Okay, so this is the concept of elementary events. Now, there is one concept called sample spaces. The sample space of an experiment is simply the collection of all elementary events, or intuitively, that just means a sample space is a collection of all those things that may happen. Of course, we only talk about basic things or elementary things. We collect only those elementary events. But keep in mind that those things that are within the sample space may occur, and those things not in the sample space has no probability to occur. Okay, if we are talking about elementary events. So let's do some exercises. Suppose I roll a dice, then the sample space is just 1 or 2 or 3 up to 6, right? The sample space is all the elementary events, and when I roll a dice, that must be 1 of 1 to 6. What if I roll 2 dices? Okay, if I roll 2 dices, then I have a lot of possible outcomes. I may first get 1 and then get 1. I may first get 1 and then get 2, and so on and so on. And lastly, I may get 6 and then get 6. Okay, so for this particular experiment, rolling 2 dices, in total you may verify that we have 33 possible elementary outcomes, or 33 elementary events in the sample space. In our previous example, we say we ask 20 consumers about how many of them are willing to buy. If we only care about the total number instead of the choice of each individual, then when I ask 20 consumers, the outcome may be 0 or 1 or 2 or blah 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 until 20. Now, keep in mind, this is the case when we only care about the total number of consumers who want to buy. Okay, if we really want to identify who are willing to buy, then the sample space would be much larger. Finally, when we are testing a new drug, what are the possible values, possible events? Effective, not effective, having some side effects, getting worse, and so on and so on. Okay, so that's about sample space. Notation-wise, we typically use S to denote a sample space. So S is a set, and we sometimes would write something like this to remind you that the probability for one event in the sample space to happen is 1. Okay, if we sum up all those possible events in the sample space, then the total probability must be 1, because one of them must happen. In general, we say a sample space is a set. If you have the idea about set theory, or you just need to use your intuition, a set is a collection of some elements, and then elementary elements are just the elements of the set, and then events are just subsets of the set. So some ideas that you may want to keep in mind. So notation wise, we say if X is an elementary set of an event capital X, then we would write X belongs to capital S, or X is in capital X. Okay, for example, getting 2 belongs to getting an even number. Getting an even number is not an elementary event, it's a composite event. Okay, it consists of 2, 4, and 6. Getting 2 is an elementary event, so we use this particular notation to say that one thing is belongs to a set. Okay, so that's about simple spaces. A simple space contains a lot of contains all those possible elementary events, and each event is a subset of elementary events. For 2 events, they may be somehow combined to create new events, and there are 2 particular ways. It's about unions and intersections. So suppose A and B are 2 events, and the capital S is the sample space. The union of A and B are written like this. So just means all those events, all those elementary events that are either in A or in B. Okay, elementary. For example, if I am talking about rolling a dice, if one event is to get 2 or 3 or 5, and the other event is about getting 1 or 5 or 6, then their union is 1, 2, 3, 5, 6. For intersection is something different. It means and instead of or. So the intersection of 2 events contains all those elementary events that are in A and in B. So that means A and B happens at the same time. For example, 2, 3, 5 and 1, 5, 6, their intersection is just 5. Okay, so that's the definition of unions and intersections. Graphically, if X is here and Y is here, then the union includes everything either in X or in Y. If X is here and Y is here, then the intersection of X and Y is just here. Okay, intersection. So the union of 2 or more events is also an event. Okay, it's just another collection of elementary events. So let's do some examples. Suppose I want to roll a fair dice. Event A is to get an even number, and event B is to get larger than 3. For even number, that means 2, 4, and 6. So we know the probability of getting an even number is 1/2. And then for getting larger than 3, that means 4, 5, and 6. So the probability is also 1/2. If we ask what's the probability of A union B, then that means what's the probability for either A or B to occur. Either get an even number or get larger than 3. Then what's those elementary events? 2, 4, 5, and 6, right? If that's the collection of even numbers and the numbers larger than 3. And then we know the union probability of A and B is 2 over 3. For intersection, it's very similar. Okay, if we talk about the same event A and B, then their intersection is just 4 and 6. And then the probability, the joint probability of A and B will be 1 over 3. Okay, so that's the definitions about union probability and the joint probability. For events, they have multiple relationships, and two special cases are important to know. Events may be mutually exclusive if there is no intersection, or we say when one happens, the other one will not happen. Okay? Mathematically, that means the intersection of A and B is an empty set. It's an empty set. Okay, so events are mutually exclusive if all their elementary events are different. For example, when we are rolling a dice, getting an even number and getting 5 are mutually exclusive. Okay, when one happens, the other one does not. Or events may be collectively exhaustive. That means A and B together, they contain or they cover the whole sample space. That means either A or B must happen. Okay? Mathematically, that means their union is just the sample space. Okay, so events are collectively exhaustive if one of them must occur. For example, when we roll a dice, getting an even number and getting smaller than 6 are collectively exhaustive. Okay, this contains 2, 4, and 6. This contains 1, 2, 3, 4, 5. So together they contain everything. Please keep in mind that two collectively exhaustive sets are not necessarily mutually exclusive. Okay, just like the example here. The first event is 2, 4, and 6. The second event is 1, 2, 3, 4, 5. They are not mutually exclusive, but they together contain or cover the whole sample space. Okay, the last concept to know is the complements. Complement just means those things not in an event. So if I have an event x, and then the complement x prime contains all those elementary events not contained in capital X. Mathematically, we write something like this. Okay, x prime is the set of x such that x is not in capital X. Okay, such that x is not in capital X. Graphically, how may we express this concept? Suppose this is your sample space. Suppose this is your x. Then where is x prime? It's here. Okay, it contains everything not in capital X. That's complements. If I am rolling a dice, then getting less than 3 and getting greater than 2 are complements. Okay, less than 3 means 1 and 2. Greater than 2 means 3, 4, 5, 6. Together, that's they are complement to each other. If I am rolling a dice, getting less than 3 and getting greater than 3 are not complements. Okay, less than 3 means 1 and 2. Greater than 3 means 4 and 5 and 6. So 3 is missing. They are not complements. In general, certainly you know the following are true. Given any set, x and its complement x prime, they are mutually exclusive, and also they are collectively exhaustive. Okay, they have no intersection, and their union is exactly the sample space. And then you probably can understand that the probability for the complement to occur is just 1 minus the probability for the original set to occur. Okay, now use some examples to help you understand this by yourself. Okay, so that's the end of the first part. Thank you.